even though I really don't think you're going to be having to do this calculation on the AP exam, you definitely should be able to go from energy to frequency, and now we're about to go to wavelength. Let me ask you one question. Why did I not put the negative sign in here? There's no such thing as negative energy, and there's no such thing as a negative frequency. That negative is just showing the direction of the flow of energy. So the amount of energy that's going to be associated with the frequency is 1.06. So that's why I just worked with that. Ross?
So how come we don't use F as the variable for frequency?
I don't know. And I personally, like if you look over here, like in the very beginning I showed you that these are the same formulas. And it was funny because I was talking to Mr. Daly yesterday and I said, I personally would rather this because this looks so much like a V that I think it's confusing. They do on the green sheet, they do distinguish between the nu, which is such a weird thing,
What did he say?
and V. And he said, yeah, I don't know why they don't use F either.
Yeah, because
Okay.
I've never seen him use C.
No. So anyway, but it's the same thing, okay? So I wish we would just use F because I think it'd be more universal and simpler, but we don't. Okay, so here we go with frequency. Now, those of you who have been doing your homework diligent, does 10 to the 14th seem like a recognizable number? A frequency that's positive, that's very much greater than 1? Yeah, okay, and a lot of times we are seeing 10 to the 14th, maybe 10 to the 13th, 10 to the 12th, but that should be common, okay? You should be kind of recognizing that. Okay, so now let's go one step further. We've got frequency. Now let's go to wavelength. Speed of light is wavelength times frequency. The speed of light, you can use the 2.998 number or 3 times 10 to the 8th. I don't care. So here's the speed of light. Nothing to memorize, just to look up. Okay? This is equal to wavelength, which is what we're going to solve for, times frequency, which is this number that we're going to plug in right there. All right? So, okay. So, y'all quickity quick, calculate a wavelength for me. One point? Is it really like 1.88? 875. Let's do 1.875. I guess we've been rounded to 3, so we should do that. 1.88 times 10 to the what? Okay. Now, a lot of people said, Ms. Herbig, when do we have to go to nanometers? When can we stay in meters? Well, technically, all I asked for was the wavelength of light. Well, if you're just answering the wavelength of light question, boom, it's there. Okay? You can do that. All right? But if I ask you what type of electromagnetic radiation it is, you have to consider your chart. Now, I gave you a chart yesterday, all right? And it looks like this. Do you remember this chart from yesterday? Okay. So if we look at this chart, we actually have 2 different types. We have 2 different wavelengths. We've got wavelengths in meters, and we've got wavelengths in nanometers. Okay? So first ask yourself, can it just stay in meters? Can you tell what type of radiation it is? Look at your chart. It might be easier to look at the one on your own handout because this might be a little blurry. Can anybody see what this radiation would be? 10 to the negative 6. This is 10 to the positive 4, to the positive 2, 1, 10 to the negative 2, 10 to the negative 4, 10 to the negative 6, 10 to the negative 8, negative 10, negative 12, negative 14. So what type of radiation is it? Infrared. It's infrared. Okay? So really in this case, we did not need to go to nanometers. Okay? But I want to show you how. Okay? Because you really should be able to go back and forth between meters and nanometers or picometers or angstroms very easily. Okay? There are lots of ways to do it. One way I use this bridge, I know that 1 meter is the same as 10 to the positive 9th nanometers. So I know that this is 1880 nanometers. Some of you might actually take your 1.88 times 10 to the negative 6 meters and say that 1 nanometer is equal to 1 times 10 to the negative 9th meters. That is fine. You'll get the exact same answer. Okay? And some of you might have a slightly different way that you do it. Okay? But you got to make sure that the converting doesn't mess you up. Okay? So now that we have it in nanometers, let's look at the part of our diagram that has nanometers in it. Okay? This is the visible light, and our vision is approximately 400 to 700, right? Where would the nanometers, 1880 nanometers, be? It'd be over here, wouldn't it? It's beyond the red. What do we call that? Infrared.
Isn't it?
Okay.
Couldn't you technically have infinitely tight, beyond gamma rays, just infinitely smaller?
Probably. Probably.
Really bad.
Yeah, really bad. Yeah, you probably could. Okay? But I do want you guys to think of what is the relationship between wavelength and energy?
Short of the wavelength.
Does everybody see that? Write that down on your paper. The relationship between wavelength and energy. Okay? And I want you to think about this. We use a lot of sunscreen, right?